Okay, I want to go back to refraction for a few minutes. So we had the picture where, and these are in your notes, but we had the picture where we were going from a less dense medium to a more dense medium, and the refracted ray was bending towards the normal. And then we had the picture where we were going from a more dense medium to a less dense medium, and the refracted ray was bending away from the normal and up towards the boundary. So I'm just going to redraw that one for a second because I want us to think for a minute about what could happen here. So here's my surface, my normal, and my incident ray. Okay? So this is my angle of incidence, and we said there a second ago we are going from more dense to less dense. So if the light was going straight through, whoops, be good if I could draw a straight line. If the light was going straight through, it would follow a path like that. But because it's going from more dense to less dense, it's going to bend upward. It's going to bend up here somewhere. Okay? So now my question is, what would happen if I made my angle of incidence bigger? Well, what should happen, because we know Snell's law, sine theta 1, n1 sine theta 1 equals n2 sine theta 2. I'm not changing my n1 and my n2, so if I make my angle of incidence bigger, my angle of refraction should get bigger, and the rays should come out like this. And so I'm going to make it bigger again. Luckily, I just happen to have different colors. And the ray will get bigger again. And hopefully you can see that as I keep increasing theta 1, theta 2 will keep increasing until finally I will come to an angle where of incidence, where the angle of refraction, the refracted ray, will go right along the surface, where the angle of refraction, theta 2, will be equal to 90 degrees. Okay? When that happens, that angle of incidence is called the critical angle. The critical angle. So the critical angle is the angle of incidence that makes the angle of refraction 90 degrees. Okay? And we'll talk about that critical angle again in just a minute. I just want to do one more step since I'm on this diagram and have all these colors. What if I make my angle even bigger than the critical angle? What will happen now? The ray will come back into the original medium. It's something that's called total internal reflection. It reflects back into the same medium. Total internal reflection. Total means all of it. Internal, back into the medium that it was trying to get out of. And reflection, because it's going to come back up at an angle equal to the angle of incidence. Okay, now for this to occur, you have to always, 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 always be going from more dense to less dense. This can't occur if you're going from less dense to more dense, because this refracted ray is bending away from the normal, right? It's never going to be up here on the surface because it's bending down. Okay, so it always has to be going from more dense to less dense, and it has to strike the boundary at an angle greater than the critical angle. So theta 1 has to be greater than theta c. Now, if you printed out your notes and you're looking at them, I did what I did here in color. I did there in 3 separate pictures, because I usually print out these notes and give them to my students. At this point of the year, we're usually running out of time, and I couldn't do colored photocopies. Okay? So when you're going from more dense to less dense, then the light can either refract into the second medium at an angle less than the angle of incidence. It can go straight along the boundary, so theta 2 would be equal to 90, or it could totally internally reflect. Now, just another little word about total internal reflection. This is actually the principle that's used in fiber optics. Fiber optics, or you probably heard in your life, because a lot of internet now, all of Bell's customers in the city probably anyway, are on fiber optics. So fiber optics are tiny little thin, almost hair-like size fibers. If you might have Christmas decorations where, the decoration has all these little wire things coming out of it and they change color. Those are optical fibers. And the way they work is that they have a core and then they have a coating. It's called a cladding. And the light ray fiber, it carries light. The signal is passed by light. And so the light is traveling inside this really tiny thin core, strikes the boundary between the core and the cladding at an angle greater than the critical angle. And because of that, it all gets totally internally reflected. Now, so this has revolutionized, really, the internet and other things because, one, they're sending light. They're sending this information as a light beam. So it's traveling at a very high speed. That's why fiber optics internet is really fast. It also means that none of the signal is getting lost as it's traveling down this beam. None of it can get out because the angle of incidence is greater than the critical angle. It all gets totally internally reflected. So it also means that when it gets to the end, to your computer, the signal's still strong, as opposed to others where it loses some of its strength all along the way. Okay, so that's total internal reflection. But we need to go back to our critical angle, because if we think back to Snell's law, N1 sine theta 1 is equal to N2 sine theta 2, we can use it to calculate the critical angle. So when theta 1 is the critical angle, this will become N1 sine theta C is equal to N2 the sine of 90, because by definition, the critical angle is the angle of incidence when the angle of refraction is 90 degrees. The sine of 90 is just 1. So this becomes sine theta C is equal to N2 over N1. Okay, so this is our equation for critical angle, which really comes directly from our Snell's law. Now, a couple little notes. So N1, like a question. Oh, let's do the example, and then I'll do a second one. So the example in your notes was find the critical angle for light at the boundary between water and air. So between water and air, and it always, always, always has to go from more dense to less dense. So it means that water is N1 and air is N2. So it's going to be 1.00029 divided by 1.333. Okay? 1.00029 divided by 1.333. Take the second function sine, and you get the critical angle to be 48.625 degrees. Now, sometimes that same question would be, what's the critical angle for water? What's the critical angle for flint glass? What's the critical angle for ethyl alcohol? If they do not tell you the second medium, then you are to assume that it's air. So if they just say, what's the critical angle for a material? It means going from that material into air. Never air into that material, because it always has to go from more dense to less dense. So from that material into air. Okay? So you'll have a few questions today with the critical angle, and probably another one or two with Snell's law and things, just to make sure you haven't forgotten them. But we do have one more thing to talk about, a little bit more to go before we're done for today. Our next thing to talk about is dispersion, and we'll have to come back for it because I think we're going to be out of time here in a second. And on the sheets that we uploaded for you, during color, this